I would like to give the floor to Mr. Revuelta, who is a senior principal at AFRY. You have the floor, and we are looking forward to your presentation.
Yeah, I think I'll...
You want to present something? Okay.
Kalimera. Good morning, everyone. I don't speak Greek. I'll go with English. It's a pleasure to be here, and thanks for inviting AFRY to present. We do a lot of studies on power market modeling, regulation. We like to anticipate regulations that are required to get where we want to get, which is a decarbonized power system. I come from the Madrid office in Spain. I've worked for almost a decade in the Spanish TSO, so I'm very familiar with all the technical issues around the blackout. I'll leave a few minutes to speak about how to not have blackouts with very high renewable penetrations. So I'll give a few ideas about renewable energies, where we are, what we see in the next few years, the challenges for renewables. Same for storage, the role for storage in the next few years to integrate all the solar and wind energy that we can develop throughout Europe and definitely in Spain and Greece. Interestingly, Spain and Greece, I think we have very similar challenges and very similar figures in relative terms. The Spanish power system is about 4 times larger than the Greek. So any numbers I mention on Spain, divide by 4, and you get roughly the figures, the similar figures for Greece. I'll say a few words about the blackout, the main ideas of what happened and what needs to be done to keep integrating more renewables in safe conditions, which is possible. It's mostly a matter of technology and doing quite some studies for grid engineers. With some role also for regulators. Regulators need to do things so TSOs can do things, so investors can do some things that bring the right technologies. And if I have time, a few ideas about the discussion around synthetic fuels and biofuels, which Europe needs to address also to try replace all the energy consumption that today is not electric. About 75 to 80% of the energy Europe consumes is not electricity, it's oil and gas, and a lot of things need to be done to decarbonize those too. So I'll start. This is just showing how electricity is what you see in the blue area. We are in Spain with similar figures as Greece, with a bit more, between 50 and 60% renewables over the blue, which is electricity. But we have a long way to decarbonize the brown, which is oil, and the brown, which is gas, and the green, which is mostly oil. And where exactly we want to land in terms of renewable penetration depends on, for different countries, on the use of nuclear, the use of carbon capture and sequestration. But I'd say that the sky is blue for renewables in the long term. Lots of renewables will be deployed. I'll speak about the challenges of the timings. Ideally, we want the timings right with demand coming at the same time as renewables, or else we can have some economic issues. This is just showing that we expect electricity systems will roughly double. What you see in the left is historic evolution of electricity demand. What you see on the right is an indicative evolution with basically power systems doubling in the next 3 decades. So again, blue sky for renewables. A lot of this energy growth, or most of this energy growth, will come from renewables, and these figures are pretty similar throughout Europe. Well, volatile commodities are an issue. I'll skip many of these. Now, I want to show, most people are very likely familiar with curtailments and low prices. What you see here in the yellow line is the typical solar production in a standard day in 2023, 2024. And this is about the limits where in some periods, typically in spring, the market does not need more energy and prices collapse because we have a surplus it's not solar that's in a surplus, it's the addition of nuclear, in the case of Spain, nuclear plus run-of-river hydro plus wind plus solar. When all of that exceeds demand, something needs to be curtailed. And actually, it doesn't really matter what gets curtailed because everyone is in a position of very low revenues. And what we show here is, well, some curtailments appear. And if we keep increasing solar at the pace at which we are developing it in Spain, which is, again, in relative terms, very similar to Greece. Spain is developing about, this year we'll possibly develop around 8 gigawatts of solar, 8 utility scale plus 1 self-consumption, slightly less than previous years, but a really strong pace. And in the next 3-4 years, as you see, we will have massive curtailments with 10-15 gigawatts of surplus renewables that the system cannot digest. There's a big role for interconnectors. I think interconnectors are a no-brainer that they are cost-effective in general. There are projects that take 8 to 15 years, but the more interconnectors we can build in Europe to use surpluses of wind in the north or surpluses of solar in the south, they tend to be cost-effective. But as you see, one message here is we are going into a situation with frequent low prices and with high curtailments, which means there is a space for integrating a lot of storage. Now, storage, what I'm showing here with this purple square is how much energy, if you think of all the energy in between the yellow and the orange line, this is basically surplus energy. It's massive. It's 10-15 gigawatts surplus energy in a day in spring for almost all the solar hours. And if we develop 2 or 3 or 4 gigawatts of storage with batteries of 2 to 4 hours, which is the standard, this is how much of the curtailment storage can absorb. As you see, it's fairly small, which means power systems in general, we're going to need a lot of storage. Not 1 or 2 gigawatts, but more in Spain, we need something like 15 or 20 gigawatts. Now, this is what we would like to have to integrate renewables and get rid of gas, both the high prices and the emissions that come with it. But I'll show how the economics of storage are not so clear. I mean, here what I'm showing is what you see on the left is the solar capture rates in Spain, monthly figures, and the last dots are the annual figures. So in the last 3-4 years, we've gone from almost 100% capture rate 5 years ago to today we are at 50% capture rate, which means that if the Spanish market trades at 70 euros per megawatt hour, PV is collecting half of that. And as you see, the capture rates keep decreasing. So importance of market modeling and price projections to make informed decisions, whether they work on a merchant basis, which is the case for some time, or whether investors seek PPAs or they wait for auctions from governments that provide CFDs, which is basically a PPA with the government. But these issues need to be understood to make proper investment decisions. Now, this is just showing how well the market can sometimes overpay, meaning that the market can pay more than the LCOE of projects. So we've been 2 years ago, we've been in a situation where the market has paid enormous amounts of money. But it's not at all impossible to go into the red zone when the market overinvests eventually, and we go into prices that are below LCOE. And this is where PPAs or CFDs with the government are important. So don't be too optimistic about investing when prices are very high, because it takes eventually 2 or 3 years. If markets are not developed properly with renewables and demand and flexibility elements coming at the right pace, we can shift very quickly from very high prices, attractive returns, to problems. Okay, red zone. Spain, I think it is now known to many investors that the Spanish system is going into a situation of low solar prices, which is likely to last a few years until all this flexibility comes. Flexibility meaning electric vehicles, heat pumps, interconnectors with France, pump storage, and of course a lot of batteries. So storage, the question is, we do a lot of fancy modeling of storage, and we model the whole breakdown of revenue streams, not only price arbitrage, which is charging cheap and discharging expensive, but also we put a lot of effort in modeling the revenues for providing services to the TSO, frequency control and voltage control. we do expect that, same as what's happening in Germany or the UK, there are very big revenues to be made providing some of these services to TSOs. The question is, how quickly do those cannibalize? Because typically there are high premiums but small volumes. So the first batteries that come to power systems, they will make a lot of money. We expect really short paybacks. But the question is, in 2, 3, 4 years' time, when power systems have lots of batteries and the TSO services are fully provided by batteries, revenues can cannibalize pretty quickly. And this is just illustrating how we model the charging and discharging of batteries. We're showing how revenues cannibalize pretty quick. The high prices can disappear quickly in a matter of few years. So this is, again, to be understood properly with proper market modeling of those revenues for storage. Another important issue is understanding what drives capacity markets, which is security of supply. And security of supply means that TSOs, they need to monitor that what we call the critical hours are fully covered. The critical hours are typically in Europe after the sunset. What you see on the right graph is basically the demand of the 4 seasons and the 24 hours of the critical days of the 4 seasons. And we show how the loss of load probability, which is those hours when power systems might not have enough energy, they are always going to be after the sunset. And if we keep closing nuclear and coal and even some CCGTs in Spain, we can have issues after the sunset. And this is what's driving TSOs to tell governments, we need some backup for these hours, these many megawatts in these given years. And this is what's going to drive a lot of the investments in storage. When some additional revenue streams are provided by TSOs because they are needed to, those revenue streams are needed to make storage happen and basically keep the lights on after the sunset. So a slide here showing on the right the breakup, the breakdown of revenues. What you see in the darker blue is day-ahead price arbitrage. On top of that, there are revenues to be made by providing services to the TSO. And if you put this in a financial model, despite the capex of batteries coming down a lot in the last few years, you don't necessarily get the returns you expected. There are many situations here. So, storage is really a case-by-case study, I would say. And what we find in general is that you need the orange bars. The orange bars is the revenues from capacity markets. Now, that's going to happen in Spain. It's going to happen in many countries. There have been capacity auctions in different places. There's, in the case of Italy, I guess the Max 8 is also providing some revenues for different flexibility and grid control issues. The issue is that these orange revenue streams from capacity markets, they will not be for everyone, but just for as many megawatts as the TSO needs to keep the lights on, basically for backup purposes. So again, lots of studies to be done on how many megawatts of storage will be needed and how many will get this payment, which makes the economics work. And we've done lots of studies on how to provide ideas for regulators to attract as much storage as we would like. Because what we find in Spain, I think this is possibly a conclusion in other countries, is we would like lots of storage to integrate all those renewables that are coming, but the market doesn't necessarily deliver that much. So either storage stops at a smaller amount, or we need to be creative with regulations that provide incentives to make that storage happen, and this can be in the form of capacity markets. There's a lot of discussion around flexibility markets. We expect for next year TSOs to come up with a number and some analysis on what the flexibility requirements are for each power system. But we need to be cautious with providing just grants and money or some revenue streams to storage because we have all these regulations around state aid preventing countries from just giving money to any amount of storage. So Greece and Spain cannot say we want 2 or 10 gigawatts of storage. We need to prove they are cost effective. So very interesting work for regulators also. I'm just showing here how those blue lines you see are situations where there is a shortage of energy, and we go into loss of load probability, and we have those typically, as I said, after the sunset in winter. But then we have lots of hours. What you see negative in those gray bars, this is renewable curtailments. So basically, we need 2 or 3 or 4 gigawatts of storage as backup to prevent loss of load. But we need 20 gigawatts, almost 10 times more storage to try and integrate renewables. So when I'm asked, in Spain, how much storage do you need? I ask back, what do you mean? Do you mean storage to prevent blackouts? That's very little. Or do you mean storage to integrate the last megawatt hour of renewable energies? And the answer is completely different. I think the right question is how much is cost effective for a system, because neither curtailing a lot nor trying to curtail zero makes sense. And we're doing quite some studies on trying to tell regulators what makes economic sense. So I think this is a bit the situation we've had in Spain, and I think countries are likely to face, where renewables come extremely quick. And if electric vehicles and batteries and green hydrogen don't come at the same speed, we can have some economic issues. So ideally, we want to develop systems where regulations and economics and flexibility all comes at the right pace. So we get both the low prices, but not ugly returns for investors. And just a few words on what happened with the blackout. Basically, I compare the blackout a bit with, don't be too scared with the Titanic. No. Although, yes, the blackout can be compared somewhat to a ship sinking. But you can see the Titanic as either it was going too fast for the control elements it had. It didn't have enough sensors and enough motors to maneuver in between the icebergs. Or you can say, well, it can. For those elements, it should have gone a bit slower. Or if it really wants to go at 30 knots in between icebergs, then it needs lots of technology. Okay? And it is possible to navigate with the Titanic in between icebergs. You just need sensors and motors, lots of things. And some of these elements, Spain will develop, and I think power systems need to develop. They look like this. It's been mostly an issue with voltage control rather than inertia. Inertia was fine, but voltage control, which is very local, you can send lots of energy 1,000 or 10,000 kilometers away with some losses, but you cannot control voltage 100 kilometers away. So voltage control needs to be very local. And a lot of these devices, a synchronous compensator, which you see on the top left, or a shunt reactor, or a STATCOM, which is basically power electronics doing the same thing as the synchronous compensator. All of these elements, we don't have any of those in the Spanish grid, and TSOs I think they'll have fun in the next few years studying how many of these we need and where they need to be located. But basically, this is the technology that can provide some of the services that renewables today do not provide. So renewables, I think, again, it is possible to keep deploying a lot. We can go into 80, 90% renewables. We just need some of these devices, and we also need the technology to provide some of those. And some people here may be familiar with the concept of grid following and grid forming inverters. I compare a grid following inverter of a PV or a storage plant as violins that follow the orchestra. They just, at some point, if we have 90% violins that do not hear the drums, they may lose synchronism. So a violin starts going off a bit, and then the next violin, which is the next PV plant, it starts doing some weird things. And grid forming inverters, and I'll stop here. Grid forming, I compare them to a violin that has a little drum inside, so it can play the music, and it can control it can produce its own frequency and its own voltage. So again, I think TSOs will have lots of fun in the next few years studying how many grid-forming batteries we need to develop in power systems. This is 5-year studies. So I recommend you start with these issues. The sooner, the better. I'll leave it here. I think I went a bit over time. Happy to take questions now or after in the coffee breaks.
Thank you very much, because we have to be also very cautious of time, because thank you very much for the comprehensive analysis, Mr. Revuelta. Just a question, you have referred to curtailments as a problem also of the Spanish market. Is there a compensation mechanism in place in Spain?
Sorry?
compensation mechanism in Spain for those who suffer under curtailments?
You mean standard curtailments of...
For any kind of curtailments.
So there are different types of curtailments. Market curtailments, no, which is basically a generation that bids at whatever price, 0 or -1.
Okay, non-market?
And for technical curtailments, part of those are, depending on whether they are produced at day-ahead stage or real-time, but part of those curtailments, they are...
Because this is an obligation under EU law.
As
regards the technical ones.
Part of them are, but we are having, let's say, 1, 2, 3 percentage points of energy suffering curtailments, which today are not compensated. Yes, we think they should, depending really on what is promised at time of investment by the regulation. But I'd say the problem is not so much curtailments, it's the low prices which are an issue. So I think interconnectors, batteries, and other flexibility elements will be key to make those curtailments, those non-compensated curtailments disappear.